Greetings everyone, this is a no-atom video. Go to noatom.com now for more of these videos. This is Group B41. We are Chris, Rodney, Isaac, Gresh, and Alex. And today we're going to talk about Hall's theorem.
Okay, so before we start, we need to go over a couple of key concepts, first of which being neighbors. So when we're talking about two different sets, let's call them V1, V2, where each of these have vertices connected by edges to the other set's vertices. If we look at two given vertices, so say over here V, this one over here U, we say that these two are neighbors because they're connected by an edge. And when we talk about the neighbor set, all we're going to do is take some subset of our V1 and sum up all the vertices within V1 to get their corresponding neighbors. So if we go back to our sets V1 and V2 with all of their edges, or vertices rather, the neighboring set of V1 is going to be all the corresponding neighbors inside of V2.
Alright, another point we have to go over is the idea of a bipartite graph. So given a simple graph G equal to V comma E, V being the vertex set and E being the edge set, we would call G a bipartite graph if we can partition the vertex set V into two disjoint sets, V1 and V2, such that every edge in its edge set connects a vertex from V1 to a vertex in V2. And so it would look something like this. The only distinctions that we need to make are that you cannot have two vertices in the same vertex set have an edge connecting them, such as this. That would invalidate the whole graph, and then that would not be a bipartition. Okay, so to illustrate an example, if we look at this graph, this simple graph G right here, we've got four vertices, A through D, with its vertex set listed right here. And you can see the adjacencies. So A is adjacent to B and D, and C is adjacent to D and B. And we can partition this vertex set into two disjoint vertex sets, V1 and V2. And V1 contains AC and V2 contains BD. And we can form a bipartition where if you take A and C from V1 and then you take B and D and put them into groups like this, and then you can show the connectivity of each vertex that we had mentioned earlier, where A and D and A and B are adjacent, and then C to B and C to D are adjacent. And this is a valid bipartition of the simple graph G.
The other point I wanted to cover before we started the theorem was complete matching. So going back to our two sets, V1 and V2, each of them have their own vertices. We can say that this bipartite graph has a complete matching if every vertex in V1 has a neighbor inside V2. Now, the things that would make this not be a complete matching, if we had two vertices connected to the same neighbor, would not have a complete matching. Or if we had a vertex that was connected to nobody, we would not have a complete matching. But on the other hand, if we had a node over here in V2 that was not matched to anybody back in V1, so if he had no neighbor, that's okay. We can still have the complete matching as long as this and this do not exist.
Now let's dive into this theorem. It's called Hall's theorem or Hall's marriage theorem, and it goes something like this. So the bipartite graph G equal to VE with bipartition V1, V2 has a complete matching from V1 to V2 if and only if the cardinality of the neighboring function on A is greater than or equal to the cardinality of the subset A itself. And A in this case would be any subset of the first vertex set of the bipartition, and this condition, Hall's condition, has to be true for all subsets A of V1. Okay, so to prove this, note that we have a biconditional here. We have a situation where we have to prove that if we have a complete matching, that it implies Hall's condition, and we also have to prove that if we have Hall's condition, that it implies that we have a complete matching. So first of all, we're gonna prove the easier implication, which is that if we have a complete matching, then Hall's condition follows. To prove this implication, let's first assume the premise is true and then show that the conclusion must follow. So let's say so we have a complete matching. We assume it to be true. So we have a bipartition. We have from vertex set 1 to vertex set 2. We have a complete matching. That's what we're assuming to be true. And now let's say for any subset A of the vertex set 1 that every vertex in A is an edge in M, and this vertex is connected to another vertex in V2 for any subset A of V1, then this implies that the vertex set 2 must have at least as many vertices as V1, because otherwise there would be some vertex in V1 that had no neighbor, and we're assuming there's a complete matching, so it's just not possible. So then this also implies that Hall's condition is met, because for some A prime, let's look at A prime, and let's just say there's some arbitrary vertex V prime in V1. Then V1 must be adjacent to some vertex in V2, and the cardinality of A prime is then going to be 1, because we have one element in the set, and we know that we have a complete matching, so this vertex must have a neighbor in V2. And so it's the cardinality of the neighboring set on A prime must also be at least 1. And so this sufficiently proves that if we have a complete matching, this implies that Hall's condition is true.
Let's take a look at an example of Hall's marriage theorem. So let's say you have a box of chocolates with 5 pieces inside, and you have a group of 5 friends. And the condition is you only want to offer your friends the chocolates if you know for sure that each of them can get a piece. So instead of figuring out which flavors do each of your friends like, there's a way we could do by finding out from them their preferences and then mapping it out using a bipartite graph. So let's say your friend A, he likes flavors 1 and 2, your friend B likes flavors 1 and 5, your friend C likes flavor 2, your friend D likes flavor 3 and 4, and your friend E likes flavors 2 and 4. So by mapping out your preferences on a bipartite graph, we can actually apply Hall's theorem to figure out whether you could get a complete matching, and which basically answers your initial problem, which is whether you could offer each of your friends a piece of chocolate. So from this, we can determine that the set A, which is A, B, C, D, E, has a cardinality of 5, and the neighborhood of A has the cardinality of 9. As you can see, it's one. There is 2 for A, 2 for B, 1 for C, 2 for D, and 2 for E. Therefore, that adds up to 9. And using Hall's condition, 9 is equal to greater than 5. Therefore, Hall's condition holds. And by applying Hall's theorem, we can determine that there is a complete matching in this example. Therefore, you are able to offer your friends, each of them, a piece of chocolate. To complete this example, let me show you the instance, because there are multiple complete matches in this situation. Let me show you one of it. So let's look at A prefers chocolate of flavor 1. So let's connect that. Well, B likes flavor of chocolate 5, so let's match that then. And as you can see, C only likes flavor of chocolate 2, so yeah, so C will get chocolate 2. And D would flavor. Let's match D to the flavor of chocolate 3. And finally, we can match E to the flavor of chocolate 4. So, as you can see, we do actually form a complete matching here in this instance. And it's definitely not unique because we could create other instances where we could form other complete matchings among the 5 friends.
Okay, so now we have to prove the other implication, because it's a biconditional. We have to prove now that when we assume Hall's condition to be true, that is, when we assume that the cardinality of the neighboring function on a subset A of the vertex set 1 is greater than or equal to the cardinality of that same subset A, then when we assume that to be true, that a complete matching must exist. And so to start off by doing this, we're going to use strong induction on V1. Since we're using strong induction, let's start by declaring the basis step. So remember, we are assuming the implication, Hall's condition, is true. So the basis step in this case is going to be when we have a vertex 1, the cardinality, be 1, which means we simply have a single vertex v prime in V1. And because we're assuming Hall's condition to be true, that is, the neighboring function on V sub 1 is greater than the cardinality of A. Okay, and so if you let A be this subset, which is just the set itself, then this would be 1, the cardinality of itself be 1. And because we're assuming Hall's condition to be true, we know that V prime must have a neighbor, and therefore the neighboring function must be greater than or equal to 1, because V prime could have multiple neighbors, so that satisfies both greater than and equal to. So we know that this is at least 1, but can be more. And that would basically mean that we've got a situation where if you look at two sets, here's V prime, and we have some nodes over here, then V prime must be adjacent to one of these, and that would be, then we could create a complete matching. So the basis step is sufficiently proved there. All right, so now let's do our inductive hypothesis. So we've got a simple graph G, and let's also say that this simple graph G has a bipartition, V1 and V2, two disjoint vertex sets. And now for some k as an element of the positive integers, let's say the cardinality of the vertex set 1 is equal to j, which is less than or equal to k. And we will then say that there's a complete matching from V1 to V2 whenever the condition, that Hall's condition, is true for all subsets of A of V1. And so now, suppose we have another graph. Let's call this graph graph H with vertex set W and edge set F. And this is also a bipartite graph, so with vertex sets V1, or W1, my bad, and W2. And let's say that the cardinality of the vertex set W1 is equal to k plus 1 elements. And so to show this inductive hypothesis, we're going to do an inductive step with a proof by cases. And we're going to have to show that when Hall's condition on the simple graph G is true, and we assume that to be true, that Hall's condition on this bipartite graph H holds for k plus 1 elements, in the vertex set W holds as well. Our first case is going to prove the strictly greater than condition of Hall's condition. And basically, from our graph we defined previously, our graph H, the bipartition with W1 being the first vertex set, we have for all subsets of this with j vertices that are adjacent to j plus 1 vertices in its second vertex set, with j being less than or equal to k and greater than or equal to 1. The second case will help us prove the equality of Hall's condition, where for some subset W prime of the vertex set W1, that for some j vertices within any arbitrary subset W prime, we have exactly j neighbors in W2. For case 1, we stated that we were going to suppose that for all integers j, with j less than or equal to k and greater than or equal to 1, that the vertices in every subset of j elements, so A being our subset of W1 and it having j elements, that it would be that every subset would be adjacent to at least j plus 1 elements in W2. And so now, if we select a vertex in W1, we'll call this V prime, and we take an element it's adjacent to, let's call this W, and it's adjacent to its. So this element W, this vertex is in W2, and now let's subtract these two vertices from the sets they were in. So W1 minus V prime and W2 minus vertex W. And as you can see, we still have a bipartition here. We've simply just removed the vertex V prime and all edges incident with it to W. And this is still a bipartition, and so now if you can observe, the cardinality of this W sub 1 minus V prime would then equal K. And that is, in fact, our inductive hypothesis, which tells us that we have a complete matching from this set to this set. And adding the edge from V to W to this complete matching produces a complete matching. So if we just simply add these back in, then we have shown that we have a complete matching from W1 to W2, and this completes the greater than aspect of Hall's condition. For the second case, we're going to have to show the equality of Hall's condition holds true. We only have to prove that there exists some subset A of W sub 1, the vertex set in the bipartition of the graph W, where A is a proper subset of W sub 1, and we'll call this W sub 1 prime. And we are going to then show that we have in this subset W sub 1j, W sub 1 prime of j vertices, such that there is exactly j neighbors of these vertices in W2, and we're going to call that subset W prime sub 2. And really what we're doing here is we're inducing a subgraph. This would be the subgraph induced, and it would take along with it all edges and vertices incident with the vertices in this subset, and we said below that that's W sub 2 prime. Now we can show by our inductive hypothesis that there's a complete matching from W sub 1 prime to W sub 2 prime. If we remove these two J vertices sets from the original graph W, by the bipartite graph W. And we're going to call that graph K. And K is going to compose, it's going to be a bipartite graph where with W sub 1 minus W sub 1 prime, and W sub 2 minus W sub 2 prime. Now, we have to show that this bipartite graph K satisfies Hall's condition for all subsets A of its vertex set W sub 1 minus W sub 1 prime. If we can't show this sufficiency, then we would have a situation where its vertex set would have T vertices, where T is going to be greater than or equal to 1 and less than or equal to K plus 1 minus J, where we minus J because we our graph W has J vertices removed from the original graph, and such that this subset would have fewer than T vertices of W sub 2 minus W sub 2 prime vertices as neighbors. Then the set of J plus T, right here, J plus T vertices of W sub 1, consisting of these T vertices together with the J vertices we removed from W sub 1, has fewer than J plus T neighbors in W sub 2. That just naturally follows because we just said that this subset of K of its vertex set has fewer than T vertices of its W sub 2 minus W sub 2 prime. So that just naturally follows. And so we would then have J plus T neighbors in W sub 2. And this overall would just contradict the hypothesis that we have satisfied Hall's condition for all subsets of A of W sub 1, which we have already assumed to be true, which if that is not true, then we have a false premise, and that would then imply always true. So we have just shown that our inductive hypothesis must hold. And so this graph K has a complete matching as a result. Now, combining this complete matching with the complete matching from W sub 1 prime to W sub 2 prime, which we showed up here, then we obtain a complete matching from W sub 1 to W sub 2, our K plus 1 variant. And all this together, via strong induction, completes our proof. All right, so this has been Hall's theorem. And thank you for
No, come on, man. Chris,
Let's try this out. So this has been another video.